of Dr. Héctor Moreno Ramón, PhD Agricultural Engineering in the Universidad Politécnica de Valencia, currently working as professor in Plant Production Department at the same university at undergraduate and master levels. Moreover, he is directly a doctoral thesis on the application of biostimulants in its improvement on the plant and soils. He develops his research career at the Valencia Center for Irrigation Studies in the Soil and Water Research Unit, directing around 20 works and final projects and dissertations on different technical subjects. In addition, he has been a principal investigator in R&D projects on soil quality. His scientific production is focused on the study of soil properties, carrying out his doctoral thesis on the hydric soils of the Albufera de Valencia. In addition, he was working on the use and reevaluating of agricultural byproducts as soil improver admittments. He has published a book and a research book chapter and has collaborated in 32 articles in conferences and 12 articles in science journals. You can proceed.
Okay, thank you very much and welcome. As a part of the staff of this university, it's a pleasure to be part in these sessions of the Stoller Chair, and it's a magnificent idea that promote this type of sessions for the students of this university. So I'm going to talk about soil quality, and the title of this conference is The Decay for a Changing Agriculture. It's, at the beginning, I'm going to talk like a didactical share in order to define what is the soil. Everybody knows what's the soil, but I think that sometimes we are focusing on the topsoil because it's the most important area for the crops, but there are a world inside this soil profile. So at the end, a soil is a natural body, and that we have minerals, organic compounds, water, and gases. And this is the key for the agriculture, so it's the basis. The soil is composed by different horizons. As you can see, we can show an oxide layer, but if we clean, we can differentiate different horizons. Sometimes we analyze the topsoil, but we have problems in the layer, in the deepest layer of the soil. So we have to take into account all the soil profile in order to improve this soil quality. And one of the best or the most important functions of the soil is the ability to support the plants. At the end, we have a lot of chemical and physical characteristics like salinity, density, mineral content that make specific characteristics for that soil that allow us to grow up different crops. The soil functions are shown here in this FAO slide, and we can say the most important related to the climate change, about the carbon sequestration. We have to provide food for humans, for the people. We can water purify and remediate the soil. We can regulate the climate. This is the most important. We have the nutrient cycling. We have everything that you need, that the plants need and the human needs. It's in the soil, so it's one of the cases. It's habitat for the organisms, and there are other soil functions that are not so important. The question is that, as you can understand what happened in the soil, we have the rocks. These rocks suffer a weathering, and they have chemical and physical changes that make that due to the soil forming factors and soil forming processes, we have the soil profiles. And this soil, with time, can advance in order to obtain horizon, E horizon, or depending the soil farming factors that we have. The natural vegetation and the mineralogy of the nutrients will allow us, or will allow the soil capacity of our soils. And why it's important to know everything about this, the soil forming factors or the forming processes? Because we have a store in the soil in order to produce what we want, the crops at the end. So we need to know everything around the soil to know how is the soil available to obtain or to obtain a good quality crops in the fields. At the end, we can find a lot of type of soils, but not all the soils can support the vegetation of the crops that we want. So if we have horizons like this horizon E, it's clear that we don't need to locate the root systems in this area, because there will be a deficit of nutrients, and the development of these plants will be reduced. So we prefer this type of red soils with limestone and clay minerals that are rich of nutrients due to the different chemical reactions in order to obtain what we want in the crops. So at the end, we have a mineral part, an organic part, air and water, and these four items will be the key in order to improve the quality of the crops, and will be the key to fight against the climate change. But the problem, as you know, is the soil is the first resource that we forgot. We are focusing on water, we are focusing on plants, but at the end is the ugly duck. So this is the main idea that I want to transfer to you, is the importance of the soil, because at the end, the soil situation is that in the world, we have 33% of soils that we have problems and are degraded due to erosion, salinization, degradation problems. In a situation in a scenario of climate change, it will be possible that this percentage will be increased. So we have to know our soils in order to fight against this situation and try to recover the productivity of the soil. This is at a level in Europe, but this is a problem that we don't know. We use a soil as the basis for agriculture, and we're not focusing on it. At the end, we are talking about soil degradation, is the change in the health of the soil. I'm going to remark that the soil is not a renewable resource. If we have problems with the soil, we have degradation processes, it's complicated to recover it. So we have to detect this type of problems, and we have to try to recover it before that we have the problem. If not, the economical invest that we have to do, it will be heavier, highest than the initial problem. So at the end, we are talking with the soil degradation, with the soil quality. That is the main topic of this presentation. It's a specific capacity of the soils in order to accomplish the functions that the soil has inside an ecosystem. But the problem is, okay, I'm going to talk about soil quality, but what is soil quality? How can we measure the soil quality? The first thing we have to know we have to identify specific parameters, indicators, like physical properties, chemical properties, or biological properties. I'm sure that the soils that you are working on, they have the specific characteristic of your area, and I'm sure that one of these or two of these properties will be increase the capacity of the soil quality, but there are another of them that will be decreased. We have to detect them. It's complicated to focus on all of them because there are a lot, but the question is, in what moment there is a change in the soil quality? This is the first question that you as farmers, as technical staff, you have to ask. And the second, in order to solve it, is what are the changes due to? This is two questions that everybody that works in agriculture have to take into account in his professional life. Because if we have to take care about these two questions, I'm sure that the quality of the soil will be good, and at the end, the yield productions will be in a good lines. There are a lot of indicators. I'm not going to focus on each one. I'm going to talk, for example, about the pH. Everybody knows the pH. We can measure the pH in several points and in several soil ratios, but we have to know that depending the pH of our soil, the availability of the nutrients that we have in the soil solution will be increased or decreased. So we have to know. And it's possible to modify the pH depending the actions, the soil management that we are going to implement. So at the end, I explain only the pH situation, but we can talk about every of the chemical, physical properties are depending of the soil management that we do. And the question is, some of the people here or in internet taking into account the soil management, or are focused on water, are focused on plants? This is the first question that I want to mark to you. Because at the end, if we want to take care of the planet, the caring of the planet starts on the ground, and change this by soil. Okay, it's the same, because if we want to mitigate and adaptate the climate change, we want to fight against this, we have to take into account the soil. And at the end, it's a balance between the resource that we have and the benefits. And the purpose of the soil quality is to protect and improve this productivity of the soil, water quality and habitats, in order to maintain the productivity that we want to obtain at the end. So at the end, we have to take care about the soil properties, the indicators, in order to obtain the most or increase all the soil functions that we can obtain with our soils. We have the nutrients, and all these nutrients are necessary for our development, for the plant development, and all these nutrients are focused on the soil. But the most important thing are in the soil, because the material, the parent material that we have, they have mineral nutrients. We have to know it, and we have to take profit of them in order to maintain this quality. So, where are the nutrients stored in the soil? We have the soil solution. We have the nutrients in the soil solution. Everybody knows about that. We have nutrients in the cation exchange sites. It's depending the availability of the nutrients. And we talk about the macronutrients and micronutrients. In the soil solutions, we have all the micronutrients and some of the macronutrients. Another we can find from nitrogen, from air, soil water, and air photosynthesis. As you know, all the macronutrients and micronutrients can be the origin in the soil or in actions related to the soil. Soil bacteria, the water in the soil, the air in the soil. So we have a store in the soil to take profit. And this is a didactical a layer that we have. For example, we have a clay sheet, and we can change. This is a layer of the clay, and normally the cation exchange situation is when we enter, we can replace one micronutrient or macronutrient by another. But the question is, when we acidify the soil, what happens? When we increase or reduce, in this case, the soil pH, we have increasing the hydrogen ions, and these hydrogen ions can replace these negative charges in the clay sheets and make available all the nutrients that we have in the clay. So at the end, if we want to obtain more nutrients for the plants, it's easier to increase the acidity of the soil. If we introduce organic matter, we are increasing the acidity, we are increasing the pH, reducing the pH in the case of the calcareous soils, and we are making this more easier, this exchange in the clay sheets. So we can change a little bit. And at the end, we have the organic matter. We have soil nutrients in the organic matter that make all that I'll say before, and the soil minerals. This is the nutrients that we have in the parent material. It's complicated to obtain, but it's a store that at the end, due to the weathering process, we can take. But the question is, what are the agriculture? Which is the situation of the agriculture now, in the future, and in the past? And we have to think that the vision of the agriculture has changed in the last time. Before the 18th, we are thinking about productivity, efficiency, breeding of new varieties, pest control, and fertilization. This is the main lines in the 18th. But nowadays, we change it. We are thinking about the production, the yield, but about the effects on the environment. And this type of situation, as a farmer, as a technician, we have to take into account. And the soil is the key. We have to try to improve the biological diversity of the soil, because it will be increased in a benefit for our crops. We are thinking about the soil degradation in order to stop it, the food quality, and the 3 R's rule: recycling, reusing, and reuse. So, these questions: what can we do to make our farms working and maintaining the quality of the soil? This is one of the questions that we have to ask. How can we optimize this resource? And if it's possible to combine this agriculture and soil quality. In the 80s, it was not possible. Nowadays, there are 3 questions that we have to take into account, and we have to try to take like principal ideas in order to maintain the quality of the soil and the agriculture in the future. So at the end, all of you, all the technicians, the farmers, know that the combination of the soil types and the land uses needs different practices. And this is local. We cannot use a technical that is used in the north of Europe, apply it to Spain if we don't have the same problem or the same characteristics or the same properties in the soil. We can use as general organic matter addition. We increase the nutrients. We can reduce the tillage in order to reduce the compaction of the soil and the erosion. We should manage fertilizer and pesticide use. We have to increase soil covers, because at the end we are protecting the soil and we are adding organic matter to the soil, nutrients, humidity, moistures for soils. We should increase the plant diversity in order to reduce this depletion of the soil, and of course we can use new technologies in order to obtain the soil quality in our farms, in our fields. So now it's changing. The soil management should modify the indicator of the soil. This is in my opinion, the main idea that we have to take in the agriculture in the future. Not change, not know it, which is the indicator or the characteristics of the soil, and once time you know it, you have to work. No, you have to manage your soil in order to improve the quality of the indicator of the quality of the soil. So at this moment, I'm going to show you 4 examples that we are working in the university, different examples or research in order to improve the quality of the soil. Here is a persimmon farm in Alcudia, Valencia. There is a management of the residue after they cut the branches of this persimmon. They cut and they introduce in the field, and we have 2 samples of soils, different samples of soils in different years, 7 years, and you can see here the increase in organic matter that we have in the topsoil and in the 20 centimeters depth due to the incorporation of this amount of residues. And what does it produce? It produces an increase of organic matter of 220% more. For example, in the topsoil, we pass from 2.67% of soils of organic matter to 8.82%. And in the topsoil, we have 2.31 to 5.09% of organic matter. We have increased the amount of organic matter. They have reduced the fertilization dose that they applied in the past due to the amount of nutrients that they have available due to this soil management. They increase the nutrient availability more than 50% in the root area, and they increase the production. And for that, they know it, that they have to make analytical or chemical analysis each year, each 2 years, in order to control this improvement and to adjust the fertilization dose and the availability of the nutrients. In addition, we can find another indicator, the soil aggregation. We have the soil aggregation here, and you can see the amount of roots and organic matter that we can find here, and the biodiversity. This is a parameter that we have increased. Here we have more water when we apply the irrigation. We have maintained the moisture for the crops more time due to this aggregation. So, and all of this has been improved due to the addition of the residues, crop residues to the field. And sometimes we are thinking about, it's complicated to know if the indicator of soils will be better or worse. We needed to make analysis of the indicators, soil indicators, to know about the soil quality. But it's not true, because we can take, wait a moment. We can take simple, wait. This is normal. Wait a moment, I will show it. I think that this is okay. Don't worry. I will show you. Okay, don't worry. As you can see in this image, we don't need to take the aggregates and send it to a laboratory. We can take both aggregates. One of them, it's used, as shown with the mouse. This aggregate, as you can see, is more dark after the introduction or the uses of residues in the field, and this is the initial aggregate that we have. We have 2 glasses with water, with a small thin layer. And if we introduce these aggregates in the soil, in the analysis that we can see in the video, this aggregate will be maintained aggregated more time, and this is disaggregated completely. So if we apply the residues and the aggregate will be compact, we have to know that the soil quality of this management that we have done is better than the initial process. So we have increased the quality of the soil aggregation, because after the soil management, in this case the advent of the residues, we have to increase the aggregation of the soil. So this is a easy analysis that we can do in our farms, and we don't have to send these aggregates to the laboratory. This is another example. This is the use as a soil improver or a biostimulant. It's a product that we can use in 2 lines. We have a sandy textural soil, and we have problems with infiltration. So we have to increase the aggregation of this soil. After 6 months, depending the dose that we apply, we have 2 products, we increase the aggregation of a sandy soil. So applying this product or this type of products, we can increase the retention of water, the water holding capacity in the soils. This is an improvement of the soil quality in this case, because we have a problem of soil infiltration. And in addition, in the case of the erosion, soil erosion, the application of this type of soil improvers make that the resistance of the breakdown of the soil increases, so the erosion will be reduced more or less than 475% of compared to the control. Another example that we have, this is the most huge, most large experiment that I'm going to tell you. It's the sample and research make it in La Pedrera, Alicante, it's near the Stoller Central. And we are talking to the soil quality and the land evaluation. We are focused here is Alicante, and it's located, this is the city of Alicante, in the Bajo Segura. And it's an agricultural area with an arid regime. And we have horticultural and citrus cultivation, okay? So we have an arid regime. So the climate change scenario will be worse than in other areas. What happened in this area? In 1973 and 1974, the IRIDA was the National Institute of the Spanish government, make a research, a study, in order to put to work all this area for agricultural objectives or aims. And they use the USBR methodology for land evaluation, and they decided that all of this area, there was 7,044 hectares capable or viable to apply the agriculture. So here we have a Torrevieja lagoon, it's a salty character lagoon, and here we have the Mediterranean Sea. So it's an area near the Mediterranean. So they decided that we have a specific area for agriculture. This is the situation in 1974, and this is the nowadays situation, current situation. Here, after the evaluation of the soil, the government made the construction of a reservoir, the Pedrera Reservoir, that supply water for all of this area. And what happens? We have evaluation in 4 years. We have several points, control points in the area, 28 soil profiles. And this was the main problem. In the first evaluation, they decided to put to work 7,000 hectares for agriculture. In the second evaluation, we detected that from the 7,000, the hectares that were working are the double, 13,000 hectares. The third evaluation in 2007, the extension of irrigatory agriculture was the double, 28,000 hectares. And the fourth evaluation in 2019, the hectares were increased. And the question is, what happened to soils and crop? Okay, this is the data from the last evaluation. We can see that this is the reservoir, the La Pedrera reservoir, and we have the pH is more alkaline, it's an calcareous area, you can see here. We have organic matter in a high and normal situation, so it's not a problem. But in 2019, we have problems with the electrical conductivity of the soil. We have more than 55% of moderate saline and saline soils. So we have a problem of salinization. This is the first idea that I want to show you in 2019, okay? We have the SAR, the relation of absorption of sodium is like the same. You think that we have here in this area a saline lagoon, so this is normal. The ESP and the carbonates are not important. But here we have the nutrients availability. We have sodium and chloride as a main nutrients that we have in all the samples that we analyze. This make problems. We have this type of pH. We have problems with calcium and magnesium variation. We have potassium sufficient in order to maintain the crops. And we have low quantities or amounts of nitrogen and pH. This is the situation in 2019. But what's the problem due to desalinization? So we have a high concentration of salts that reduce the water absorption and the capacity of the roots due to the sodium and chloride. And we have antagonist effects. We have high concentration of sodium and chloride that make a deficiency in the absorption of potassium, phosphates, and nitrates. And the potassium deficiency it's important for the formation of sugars, fruit size, influence of the weather condition, and regulate the CO2. So the high levels of these two nutrients make then the citrus, in this case, reduce the size of the fruits and other problems that they show it. So if we analyze the indicators, we can see that during the 5 years of analysis, the pH is the same and the carbonate is more or less the same. So these two soil parameters are influenced by a parent material factor because it's a carbonate area. But what happens with the organic matter? In the years before 1997, the amount of organic matter was very low in the highest number of soil samples. But after the 2000, there was a change in the soil management that make the incorporation of the residues that make that the amount of organic matter increases. So at the end, this is due to this characteristics is due to a parent material factor, but there are factors that can be influenced by anthropic factor. And this is more important. What happens with the soil salinity? Here we have a salinity, and this salinity increases in 1997, decreases in 2007, and now it's increasing. And this is related to an anthropic factor or a climate factor. As you can see, here in 1999, we have a reduction in the rainfall, and we have higher temperatures than the average, the normal average. And we have an increase, so in these years, there is not a problem of scarcity. So at the end, we have a problem with the climate change factor, but we have anthropic factor that make that the soil quality in this area will be decreased. And this is the question that I have at the beginning. What happens to soils and crop? So in the first evaluation, we have 7,000 hectares, and the government grants an endowment of water to construct a reservoir construction. So we have, for this amount of area, for this area, we have water. In the second evaluation, we increase it the double the hectares. So we don't have enough water, and we construct several pumps in order to extract water from the aquifers in order to supply the water that we don't have due to the increases of the area. In addition, we have drought and lack of water resource, and they make it that there are another pump illegal constructions that arrive to the more deeper aquifer. As you remember, we are in an area near the Sea Mediterranean. So at the end, due to this depth of the pumps, we start to supply water, saline water. So in this area, the increases of the electrical conductivity was due to the application of water saline in order to supply water for our crops. This is the main reaction. We have salts on the soil, and in order to improve or to solve or to recover the soil, we increase the leaching fraction. We increase the drop of water, the amount of water, and we, at the end, we saline inside the fresh aquifer. When they detected that, we changed it. We detected this type of salinization process. There was the abandonment of the citrus oranges, and the government stayed to use the wastewater in order to leach these salts. This make that the electrical conductivity of the soil or the soil salinization will decrease, but the problem was that we increased the double of the hectares. So at the end, in the last fourth evaluation, we can see that we increased the agricultural lands, and we are at the same moment at the beginning. We are trying, due to the scarcity of water, we are starting to salinize the soil. So we have recovered the soil, and we have decreased the soil quality at this moment. And this is nowadays the current situation. We don't know in the 2 or 3 years what it happens. Everybody knows about the problem, and they know that they have to recover. But this is not a normal cycle, because the soil quality suffer a lot. So at the end, we can find this is the same the ESPO, the SAR, the same tendency or trend than salinity. But at the end, we are making a degradation of the soil, because the sodicity, they break the physical structure of the soil. They sail in the pores, so the infiltration will be reduced, and we have a lot of problems in order to move the nutrients in the soil. So at the end, we will collapse the soil. So at the end, we analyzed the USBR methodology. We analyzed in 2009, and this is the most important thing that I'm going to show. This is the situation of this land evaluation in 1974. The green is the best class for agricultural development. And as you can see, in 1997, we have points that were not recommended for agricultural. There was a decrease in the soil quality. In 2007, we improved a little bit this quality, but nowadays is the same. As you can see, the quality of the different class for the evolution. So if we analyze the soil quality between 2007 and 2019, there are 29% of the sites of the soil profiles that has a favorable change. There are another that are equal, we have in the same situation, and there are 80% of soils that they have an unfavorable situation. So it's a problem that we have to know and we have to try to solve it. This is, in general, the main ideas. Soils are a renewable resource. We have the overexploitation of the resource in area with a deficit of resource we have taken into account. Salination and solidity are one of the most important degradation processes due to the climate change and the loss of quality. And the balance of the total nutrients make it antagonistic effects due to the amount of calcium and nitrogen. So at the end, quality indicators must be controlled constantly during the farm working. And this is quickly explanation. We can try to analyze. We can try to use indirect measurements of soil quality. For example, the use of new technologies with image treatments, color measurements. We know that the minerals, they have the weathering process, they produce inorganic compounds, cations and anions. This is the main minerals. And we can find in an area, in a specific area, we can make the maps of the concentration, for example, of iron, nitrogen, and salt. And we can try to relate these chemical properties with the values of color, like chroma, like lightness, and we can obtain pedotransfer functions. We can measure the soil, and we can know which is the concentration of the nitrogen, of the iron, of the salt that we have in the area. Which is the most problem that we have? For example, for the Spanish semi-arid soils, we have problems of nutrients. With the color, we can control the soil quality, and we can analyze the amount of carbonates. So if we have acidity, we have calcium, we can control the electrical conductivity, the shock, or the iron. But the problem is all of these measures will be due for our local soils. It's not useful for another soils. It's not used in other situations. So it's a simple methodology. We can take a photo with the color, determine the levels of the soil contents. It's easy, quickly, and effective for our local conditions. It's making to remark. And at the end, as a general idea, I want to make that the soils is the key for change, the climate change. We have to improve the soil quality. We have to necessary to schedule the continuous soil analysis. We have to control the analysis of the soil. It's the basis of the agriculture. We have to control the fertilization, because if we have calcium in the soil or magnesium in the soil, it's not necessary to add nothing. In arid and semi-arid soils, we have to be careful by natural threats, the increase of temperature, the stress of temperature that we're talking this morning, or water stress. It will be higher in these areas than in other, and we have to improve or to maintain the organic matter. The salinization and the soil degradation are, in my opinion, the main problems that we have in these areas. We have taken into account. And this type of salinization can be due to the natural conditions or the irrigation that we add. We have had organic matter depletion due to the temperatures, the higher temperatures that we hope due to the climate change scenario. So we have to maintain the organic carbon content in the soil. You see that low organic carbon in the soil, low nutrient content in the soil. So at the end, it's a control of the nutrients. We can manage fertilizers and pesticide use. We have to reduce. We have to increase the soil biodiversity. And in the case that we can use, we can crop the rotation. If we have trees, fruit trees, we can add some special of green manure in the field in order to increase the soil biodiversity and the soil amount of organic matter. And we should monitor and use new technologies in order to control the nutrients and the soil degradation or soil quality. So at the end, the soil quality, it has a social dimension because it depends the plant, animal, and human health due to the yield and the production of the fruits or food. It's an economical dimension. We have a biological productivity. If we have a decrease in the soil quality, the economical cost will be higher because we have to recover the soil quality, and the environmental dimension because it's a thing that we have to take into account. We don't have to deplete or degrade the resources, the soil in this case, because at the end it's complicated to recover. So thank you for your attention, and if you want some questions.
Okay, this is turn for questions. Any questions in the room for the attenders? Just one.
Hello. Yes, my question is, what is your opinion about applying a biochar in the soil?
About, sorry?
What is your opinion about applying biochar in the soil?
Okay.
Because you say that you incorporate residue. How you incorporate the residue is the second question, and what type of residue you incorporate. Because no-till farming by far shows that per year they also have residue on the ground, which is incorporated in some respect. The soil organic matter, you could increase it by 0.1% per year. So in 10 years, you could increase it with 1%. Here you show a huge percentage. So by incorporating a biochar, my personal belief is you are going to increase it recently more. And what do you think about mixing a little bit of biochar with wood vinegar?
Okay. So biochar is one of the options that we can incorporate in the soil. It's a good solution. I want to mention that it depends the amount of organic matter that you want as a short term or long term. For example, as you asked me about the type of manures, we can apply fresh manure, we can cut and we can put, and this is depending the conditions, the temperatural, depending in the area, the amount of organic carbon, organic matter that arrives to the soil will be higher or less depending the conditions. But the fresh matter, if the degradation is higher, we have the nutrients available easily at this moment. Biochar, for example, there was a treatment, so the carbon is more related and is more available in order to take it by the plant. So depending the terms that you want to apply.
What about the wood vinegar?
The wood vinegar?
Wood vinegar. This is a liquid which is about 200 substances, and this is going through a pyrolysis process. It's part of the pyrolysis and biochar. You could get biochar, only biochar, or some different substances, one of which is the wood vinegar.
I don't research about wood vinegar, but at the end you have to know the amount of carbon organic that we have to add in that sense. I don't know the specific content of this.
High acidity liquid, 3.4 stuff, which could be applied to dilute it in water
Yeah.
by 1 to 100 because it's very concentrated and it makes the biochar very alive. Some certain research is not only.
Yeah, it depends. It depends. In attention, it depends to the conditions of the soil biodiversity in this question too, because it's clear that if we want to have carbon directly, as you can apply like water, and you can take it directly for the plants in that sense, or you can apply another type of manure that can stay more time in the soil.
But you apply the manure, you say, or any kind of residue.
Yeah.
How you apply it? On the top of the soil or inside the ground? You incorporate it.
Okay.
This is very important.
Okay. You can apply, here for example, we can apply on the topsoil because we have the problem. You can incorporate, but it depends too if you have erosion problems, wind erosion, it depends on the situation. If you incorporate in the soil, you can apply the manure, the wood, and you can make a slight clothing in order to incorporate to the soil. But for example, I show you that applying only in the topsoil, there was an increase in the topsoil, but in 20 centimeters, we have an increase in several years of 3% points in the soil, in the depth.
Yeah, because,
so it's better to incorporate to the soil.
Because there is a German research conducted a couple of years ago, and it shows that the root mass left from cover crops leave over 50% and becomes or turns into carbon. But the stuff which is above the leaf mass, it is only a very small percentage which converts to that. So if you apply some, it should be mostly in the soil.
But at the end, for example, in this field that I show, at the end it's an economical question. If you have to incorporate to the soil, you have to add a cost that you don't have in the order if you put and you cut. So it depends the farm and depending the situation, but it's better to incorporate in that sense because the oxidation of the soil, of the organic matter will be reduced and maintain more in the soil that if you are left in the upper part. Okay.
Any other question? Well, Héctor, I have a question for you.
Okay.
As you can imagine. Talking with you during the break, I completely agree that soil is the great forgotten. Even more when we are considering all the key points for nutrient use efficiency or water use efficiency. But how much limiting do you think that it could be in decision making for a crop development in a specific area?
Yeah. It depends the specific area, but it's true that, in my opinion, there are highest area to research about the relations between the root system, the rhizosphere, and the soil in order to improve the efficiency of taking these nutrients. It depends on the situation. We have, for example, the salinity situation, we have to leach these salts, but at the end there are nutrients that can be useful. If we can improve these channels to the plants or reduce this type of stress, I think that it will be better in order to obtain a better nutrients availability in the plants. But I think that there is a specific area that we have to research, this small area, this rhizosphere between the roots and the soil in order to improve the plant physiology of the plants.
Thank you. One more question.
Yeah, I have one question. What do you think, or what is your opinion about what is going to be the role of all these new biologicals that now are becoming a trend to use to incorporate into the soil and to improve? Are they going to improve the soil? Do you see some biologicals more useful to fix nitrogen or to activate other nutrients in the soil? What do you think about the biologicals, and what is your recommendation about them in now, present, and the future?
I think that this is the key, because I'm talking about the soil quality. I talk about everything. When we talk about the soil quality, the first parameter that we think is about the chemical parameters. And it's easy to apply some chemical products in order to improve this quality. But at the end, if we want to increase in a large time the quality of the soil, we have to improve the biological quality of the soils. And in that question, for example, we can apply some chemical product, but in my opinion, if we try to improve the soil biodiversity, the amount of macro and micro fauna that we have in the soil, at the end, the crop and the quality of the soil will be higher. And in this question, I think that it's the key in the future to use the biological improvements of products in order to improve this. And in this question, I read another. We should know what happened these biological products that make that the roots for the crops increase the yield productivity or reduce the stress, abiotic stresses, water stresses. This is the key for the future, I think. But I think that the future is the biological products applied to the soil because they increase the quality and all the other things.
One more question.
Mr. Hector, I have two fast questions. The first one, because before I was working with organic matters, trying to improve the biological properties of the soil. And do you consider, because normally when we make an analysis of the content of nutrients of the soil, of the organic matter, we look only the percentage of organic matter. But there's a lot of functionality and depends on the kind of the organic matter. If you have a higher content of labile carbon,
fulvic acids.
Exactly.
Like
and we were looking that was relation between the higher activity and higher population of some beneficial microorganisms if you have higher concentration of fulvic acids, or carbon, labile carbon. So at the end, do you consider that it's not only a question about, this is the question, it's not only about to add organic matter, I think it's what kind of organic matter are you adding to the soil? And regarding the other question, if you agree with that or not, it's good to add microorganisms or to make them work more what you have on the soil because they are more adapt to your soil conditions? This is the question.
Okay. The first, I told you, there are a lot of parameters that we analyze. The normal parameter is the organic matter because you know, and I'm told about the organic matter as a simple parameter, but for example, one of the parameters that we should analyze is the respiration of the soil. This is the key. I'm sure that if I add organic matter, there will be increase the macrofauna, microfauna in the soil, and I'm sure that there will be a higher increase, an increase of soil respiration. This is the key, because we can analyze at the beginning the soil respiration after the addition. If they have increased it, we have a soil quality parameters. We can talk about the different parameters inside the organic matter or the carbon-nitrogen relation. We have a lot of parameters. We have labile. We have, when we add biochar, it's not the same add to biochar like manure, fresh manure or wood. It depends, but it depends the resources that you have and the economical cost that you have. For example, in these fields, they cut the branches and they put on the soil. The cost is like a zero. If we have to buy biochar, we have to produce biochar and include the cost, it will be higher. It will be better, it will be possible, but at the end it's an economical situation. And the second question about wait, I'm thinking. And okay, yeah.
One microorganism or to make them work with inductors?
Yeah. It will be better that the organism use that in the soil, because sometimes you try to introduce the organisms that they doesn't appear in the soil, and they have problems because they don't have resources in order to development. So it depends the situation. It's true that sometimes you introduce a specific non-local microorganism, but if you add organic matter and you have food for their development, there is not a problem. But it's better that something that has adapted to the local conditions is better. In that sense, I think that the technicians and the researchers have to try to look for these microorganisms adapted to the area. So they have to develop it.
Okay, so that we are going to move forward to the next presentation. Thanks a million, Héctor. Next presentation will be the final one, and it will be developed by Dr. Ryan Miller, BS degree, major in horticulture production with focus in citrus production, and minor AG Business Management in Florida Southern College. MS degree by University of Florida and PhD degree by University of Arkansas. Currently working as a director of Applied Research North America's Stoller Enterprises, as responsible for design, development, and implementation of technical programs and strategies across the North America region, Canada, USA, and Mexico. In his work experience, has developed issues in plant nutrition with agrochemical, biologicals, insecticides, and herbicide actions on different extensive crops with companies like Compass Mineral, Corteva AgriScience, or Agriculture Division of Dow DuPont. And even more, with greater number of professional societies as Florida Fertilizer and Agrochemical Association. He has been member of Crop Protection and Fertilizer Advisor Committees in Florida Fertilizer and Agrochemical Association from 2019 until today. Dr. Ryan Miller has edited 13 referred manuscripts, 8 newsletters and extensions publications, and has collaborated in 50 abstracts or proceedings in a regional or national meetings. Ryan Miller will develop his presentation, Food to Thought, Science, Technology, and Sustainability, where we can identify the clear importance of science implementation and data compilation in farms for the decision-making along the crop season. Come proceed.
Thank you, Vicente. Can everyone hear me okay, even in the back? Yes? Okay. I would ask the folks online, but I assume they can hear me well also. I just want to first, before I get started, I just want to say, first and foremost, thank you for everyone's attendance today and sticking around until the last presentation of this event. It's also my honor to be able to be here, to be able to chat with you a little bit on some of the topics and some of the research focus that we have within Stoller, and also contribute to this first Stoller Chair event. So thank you for your participation and the invitation. In regards to my presentation today and some of the topics that I'm going to try to spend the most amount of time and emphasis on, many of the presentations yesterday and today hit on various topics related to plant physiology, an excellent presentation on soil science as well. So today I'm going to try to be fairly broad in the focus of the presentation, touch on a few different topics, and also just try to provide a little bit of insight into some tools, into many of the projects and technologies that we're working on at Stoller. These will be some of the primary topics that we'll focus on today. So first and foremost, I'd like to just at least hint towards scientific achievements and advancements. So where are we today? When we say the word science and scientific advancements, what's around the corner? What things are coming? I feel like anytime we get a group together like this where we're focused on science and physiology, it's always really important to make sure that we're looking ahead, right? Let's have an understanding of the past, the present, and also the future. I'll also touch on technology. So a large portion of my presentation today will be focused on digital ag, the power of digital ag, how Stoller is utilizing and harnessing the ability of digital ag, and what that means for water use efficiency, nitrogen use efficiency, how it plays in this climate change environment that we're in today. And ultimately, it is a key project as well. As you can imagine, we have many projects at Stoller, but it is one project that we're focused on as well from a global perspective that I want to make sure we emphasize today as well. So first, before we get started, let me lay a little bit of foundation with just scientific advancements today. Before we get too far into the science, it's always important, I feel like, to understand our challenge, right? For those of you who were in attendance at our Stoller Experience event, Vicente Dominic gave an excellent presentation around all of the variables that we face today with climate change, with adaptations, just heard a lot of variables that impact just the soil. We also have a growing population, right? That growing population is part of all of our job security in a way, because we have to focus on how to improve our crop production, how to improve our sustainability in order to feed a growing world. So this is obviously our challenge, but how do we address our challenge? There's many things that we could discuss in this time today, in this presentation, but two of them are going to be science and technology. And when we say science and technology, personally, I view these as two different topics. I view science as the rapid innovation, all of the new products, the new discoveries, the new patents, the new products that you see get launched by companies similar to Stoller and others as well, all the recent research that gets done at the university level and people across the world. That is the scientific achievements that I'm referring to. When I think about technology, I think about technology in the form of tools. What are tools that we can use to help us learn more about the science that we have discovered, right? So as an example, we're getting a lot of advancements in robotics, we're getting a lot of advancements in remote sensing, and also digitization. So this will help lay the foundation for some of the slides that will come in my presentation. Three key advancements that we see today. Everyone in here, I believe, probably has a cell phone at some way, shape, or form, correct? Most of us operate on some sort of satellite network, whether it be 3G connectivity, 4G connectivity, 5G connectivity, depending on what you have today. Well, I'm here to tell you 6G is coming, 7G is coming, 8G is coming. Connectivity around the world is going to be increased tenfold from what we already have. If we just take a second to reflect, 15, 20 years ago, we didn't have text messaging. Email wasn't really the primary means of communication. We couldn't pick up the phone and call someone as effectively and efficiently as we can today. So that's one big tool, just connectivity around the world is going to increase. And the connectivity portion of it is going to rely on our ability to communicate with each other to be able to learn on a global scale. So that's one big piece. Drone farming is something that's also becoming a popular topic. We'll talk a little bit more in depth about drones a little bit later on. Smart equipment. So there's already advancements in that as well. There's tractors that can drive themselves, sprayers that can drive themselves. The automation of crop production is starting. We've already talked about this morning, we heard the presentation about greenhouse production and the advancements there. Water collection, right? And then smart crop monitoring. We're going to talk a little bit about sensors as well in the presentation. And all this is driven, again, by connectivity. So once we learn from each other about the tools that are out there, that's my ultimate goal for this presentation today, is that we have a clear understanding of the tools that we have available to us, and we have a clear understanding of how we can use those tools to talk about science and talk about our product innovation and launch. So what is sustainable agriculture? We're going to reference sustainable agriculture a few times in today's presentation. I'm just going to read. I'm not a big fan of reading presentation slides, but I will read this one quote from the USDA because I believe it's important. So the USDA defines sustainable agriculture as an integrated system of plant and animal production practices having a site-specific application that will, over the long term, satisfy human and fiber needs. The key part, I believe, in that personal phrase is that we have an application and we have something that's long-lasting, right? Sustainability is not sustainable if it doesn't last for a long period of time. That's key. If we come up with a short-term miracle solution that works today, we need to make sure we continue to study that solution over time to make sure it continues to provide what we know it can produce today. So some goals that we work on, not only at Stoller, but as a scientific community. Many of us are familiar with these topics. We're focused on increasing farm gate profitability. We're interested in promoting environmental stewardship. Our industry, whether we realize it or not, gets a black eye in many topics around the world because we talk about the environment day in and day out. We rely on the environment day in and day out to produce food. So it's key that we focus on environmental stewardship. Ultimately, we're trying to enhance the quality of life, right, for everyone around us. That's not only for our family personally or ourselves personally, but for our communities, both locally, regionally, nationally, and internationally. With ultimately, as I mentioned previously, the whole goal here is to increase food production, right? That's the key in sustainability as well. This slide is becoming one of my favorite slides to present for a couple of reasons. So the very first time I gave a presentation utilizing this slide was at the World Biostimulant Congress in Miami, Florida. And in that conference, it's filled with industry representatives. So there's not a grower focus there. There's not really a university focus. It's all industry collaborations, right? So it's all people like Stoller and other companies as well. So when I shared this slide, I asked the audience. There was about 250 people in that room when I asked the question. I said, when you look at this image, what do you see? And I was very quiet, and I let a few people chime in. And of course, one of the first things they said was, well, I see some weeds in the row middle. Maybe that particular grower needs a herbicide application. Okay, that's fair. And they said, well, somebody else chimed in and said, maybe they need some irrigation. They looked along the tree line here and they see some microjet sprinklers. I said, okay, what else do you see? I said, well, I also see, looks like the trees here. For those of you who are not aware, this is an almond crop in California. I said, well, it looks like the almonds, looks like maybe they're a little bit light green. Maybe they need some nitrogen to green them up a little bit. I said, okay, well, this is what a grower sees. A grower sees the things that you cannot see or you cannot identify, right? They see the stress conditions, both biotic and abiotic. They see temperature stress, they see water stress, they see labor shortages, they see challenges, right? So we have to use, and this is Stoller's approach to how we develop products and how we come up with solutions, is we try to make sure we use the lens of a grower when we're coming up with our solutions. Ultimately, science and technology can help mitigate all these stresses while improving yields, quality, and sustainability. That I'm confident in. However, the answer is not easy to find, right? So I'm going to share a little bit of information on how we can address things like stress science as an example. So this slide here, we've talked about plant physiology, we've talked about soil science. There's a lot going on in terms of stress science within the plant itself. We heard a presentation today around temperatures and around how that can have impacts on plant hormones and other things in the plant as well. That's a key abiotic stress event that we see. Water, we just had a great presentation on soil and water quality and what that means in terms of the plant itself. Water deficit and flooding can have massive impacts on the plant itself. There's also this column with biotic stresses, right? So all the living stresses, the insect feeding, the diseases, any sort of weed pressure, all those living things that can impact the ability of that crop to be effective at producing something that ultimately us as humans or animals that we feed, that they need that crop. So stress science is not only a complicated science, but it's also a science that has a very large impact on the ultimate result of that particular plant. So let's shift and talk about technology. I'm going to share with you the next few minutes some examples of how we can use digital technology to help us understand not only performance, but also understand some of the stresses that we just shared on the previous slide. Whether we realize it or not, I've already alluded to this a few times so far in the presentation, but we have a massive amount of digital tools at our disposal. And I'm going to share with you 4 primary tools. And when I talk about these digital tools, I like to start out the farthest away from the Earth's surface and work our way back down to ground level. So the first image I'm going to share with you is around satellite imagery. So whether we realize it or not, every single day, all the time, 365, 24/7, there's around 6,500 satellites constantly orbiting the Earth. So these satellites can not only tell us things about what's occurring here at Earth, they can also give us really valuable feedback and predictive indices around crop physiology and performance. Airplanes. Many of us have been on airplanes before, if not recently, to travel to this event. So airplanes are also an important tool to understand around digitization. At any given point in time, the FAA says that there are around 9,000 airplanes in the air. So at any given point in time, 365, 24/7, around 9,000 airplanes in the air. Drones. Drones are becoming increasingly popular, right? Just like biologicals are becoming an increasingly popular topic, drones are becoming an increasingly popular topic. Drones have a lot of advanced capabilities, but each one of these you'll start to find there are pros and there are cons. There are advantages and disadvantages to each one of these digital tools. Drones have a very nice ability to collect a high resolution, very detailed image at the ground level. However, there's a lot of logistical challenges with drones. If you had bad weather, you have to physically also have someone there at the location to pilot that drone as well. They also have batteries that don't last typically more than 30 minutes to an hour. So there's cons as well with drones. And at the ground level, of course, we have sensors. So sensors, when I'm talking about sensors, it could be a EC sensor, it could be a moisture sensor, it could be a thermal sensor, infrared. There's a lot of different sensors that we have at our disposal today. And the cost of these sensors are also getting very affordable as well. So we can start to incorporate sensors into much of our research, especially at the small plot level, and ultimately be able to translate it over to commercial operations so that they can have a clear understanding of performance as well. So today's presentation, I'm going to share an example of each one of these different digital tools and how it can tell us something about the performance of our particular research that we're looking at. So let's start off with satellites. So when we talk about satellites, just from a high-level perspective, the pro of a satellite is that you don't have to go anywhere to access satellite imagery. You can sit at your desk in your office or at your home at the convenience of your computer and click away, and you can get that satellite image. The con, or the disadvantage of satellites, is that the accuracy is typically not the greatest. So they're typically 3 meters of accuracy. So that means that when I see in this particular image, which I'll describe in just a moment, when we see red or we see green, that indicates bad or poor health. Green indicates good health, right? So a healthy crop. That pixel is 3 meters accurate. So that means that if I'm standing here and that pixel is green, the greenness may be here or it may be 3 meters away from me. So it's not very accurate in terms of where actually that is occurring, but it is a nice tool for convenience, and it's a nice tool for the large scale of the image you can collect. So this particular field is a hazelnut field located in the Pacific Northwest region of the United States. And one of the key areas I want you to focus on is the area in black. So this particular rectangle that we have here, because that would be the treated area. What's not important in this picture is what the treatment is. I wouldn't want to focus on what the treatment is. However, I really want to use these next couple of slides as just a tool to show you how satellites can pick up a response that a treatment can provide. So in this particular field, this area was located just as a demonstration area. This is not a small scale replicated research trial. We're not trying to collect statistical analysis or anything like that. We were just trying to prove a concept to this particular hazelnut grower. The date of this application was June 24th, and on this day, the farmer applied a recommendation of a product. The daily high this day, which is important to note, was 90 degrees Fahrenheit. So this crop, hazelnut, optimum efficiency for hazelnuts are around 85 degrees. So it's already in an environment where it's not photorespirizing in an effective way. So June 24th, date of the first application, I want you to focus on the rectangular area. 10 days after application, what do we see? We start to see some green responses. Looks like there's more consistent health across that entire treated area. Keep in mind, this is 10 days after application. The daily high this day is 91 degrees Fahrenheit. So again, still above what's optimal temperature for that particular plant. What I did not show you was the difference between day 1 and day 10 and all of the daily highs in between. There was multiple days where 100 plus Fahrenheit temperatures were reached. So a very hot, very stressful period. Let's move 10 days out. So now we're 20 days after application. We see even greater deep green response, indicating that that solution, that product that was applied, or products that were applied, ultimately is helping give response. It's helping elevate the health of that treated area. Now we fast forward to 30 days after application. Now we start to see things start to go the other way. Right now we're seeing the plants start to stress again. We're starting to see the high temperatures. Today is 88 degrees, still a little bit above the maximum optimum threshold. So we're still stressing out that plant a little bit, and we're starting to see things start to go in the opposite direction. So this is telling us two things. One thing is telling us, okay, we see a response from our particular application in terms of health increase, but we're also starting to realize that there's probably a maximum application window of when it starts to maybe not be as effective, where maybe a secondary application may be warranted, correct? So July 23rd, we look at the image and we see this image and we pick up the phone, we call the grower, say, hey, Mr. Grower, you might want to consider making a second application. And the grower says, okay, no problem. Most of us realize the complexity with farming. So ultimately, it was July 23rd when we recommended a second application be made. August 4th was the day the grower actually made the application. So it took him almost 2 weeks before he was actually able to make the application. At this point, the situation has gone pretty bad. You see very high stress across this entire field, especially in the area here where the treatment area was. It looks like this crop is stressing pretty bad. Very low health quality. The daily high this day is now 97 degrees Fahrenheit. So this plant is stressing, and it's stressing at a very high level. So this is August 4th. A second application of the technology was applied. 20 days after that application, we see response again. We see response in that treated area. It looks like it's starting to recover from that stress event. So why is this important? A couple of reasons. Number one, we use the satellite to help give us an indication of when we might need to make an application. That's very powerful because our naked eye could not detect that stress. When the grower walked out to the field, if I back up one slide, when the grower walked out to the field, he was happy. He said, this crop looks good. His eye could not detect what the satellite imagery could detect. So this tool, satellites just as one tool, are not only helping us get an idea of when stress is occurring, but it's also helping us see that whatever the solution was that was applied seemed effective at replicating or helping reproduce the photosynthetic level and metabolic rate within that plant to be a little bit lower suppressed level. Ultimately, me as a scientist on the R&D side of the organization at Stoller, I'm concerned about data, right? So I want to know, what did the data say at the end of the trial? The image is great. For people who are visual learners, that's a nice tool, but ultimately, did it help gain profitability? Did it help improve yield? Most of us understanding stress physiology, understanding plant physiology, we understand that if you have a less stressed plant, generally speaking, you increase yield, correct? Because of the Stoller treated area, we were actually able to increase yield about 1,000 pounds. That 1,000 pounds of hazelnuts was worth about $1,000 to that particular grower. So just in that treated area, he was able to increase his profitability because he made a couple of applications of technology, and he also made timely applications of the technology that were afforded by the satellite, right? I'm going to move past the satellite, and I'm going to go a little bit closer now to the ground level. So now I'm going to share with you a drone example. So this particular example is again in the United States. This is actually in California. And again, what I would not focus on is what the particular treatments are because they vary. But the most important thing is to understand what is untreated and where do we have treatments and what is the satellite sharing with us. Again, in each one of these different tools, I think it's important that I demonstrate what the pro is or what the advantage is and what the con or the disadvantage is. From a drone perspective, when you look at this image, there's 3 actual beds of strawberries that run east to west in this image. So you see the first row, the second row, and the third row. And strawberries are typically planted next to each other in a side-by-side planting scheme all the way across those rows. Each one of these colors, for those of you who are in the back of the room, it may be challenging to see, but for those of you who are a little closer to the screen, you can identify these are individual circles. Each individual circle is an individual plant health reading. So this is an extremely accurate tool. I talked about satellites being a 3-meter accuracy. Drones are sub-centimeter accuracy. So we can actually look at per plant, per leaf response from NDVI, NDRE, thermal, LiDAR, many different measurement parameters and many different mechanisms in terms of collecting data. So the important thing here is that, as well as the fact that you can start to differentiate when we look at our mean, so across all of those different treatments, across all plots, we were able to collectively summarize what the mean NDVI value was. Now I mentioned I'm going to emphasize pros and cons. I said a pro of satellites was that you can click on it at your computer every day, right? A con with drones is that you have to physically be there in the field. So our approach for this particular trial was to try to understand if we're able to collect imagery that shows differences. We have to go there at very strategic times in the year. So strawberries have a long harvest window. Oftentimes they're harvested 30, 40, sometimes 50 times before the crop is finished for the season. So we went to this field 5 different times throughout the end of the season. So you see here March 12th, April 15th, May 15th, June 16th, and July 8th. Now if you see here where we have a control treatment, you see a Stoller treatment and a Stoller treatment. Again, I wouldn't focus on what the treatments are. The most important thing is to see that at this particular stage in the plant, we didn't see any significant differences. It looked like the health across the control treatment and both of these Stoller treatments were consistent. There's no statistical differences here, right? They all have a letter A, indicating there's no significant differences across the means. However, what's important is when we get later in the season, I mentioned strawberries are harvested 30, 40, sometimes 50 times before the season is done. What we do see is a healthier, generally speaking, a healthier crop later in the season. That later in the season healthier crop is also indicating that we have higher yields. These help answer really important questions. So if a grower or a customer came to someone at Stoller and said, well, looks like Stoller treatment 1 or treatment 2 or whatever the treatment may be, doesn't matter. Looks like that treatment improved my yield by X amount of pounds per acre or X amount of kilograms per hectare. How did it do that? We can always answer the physiology questions behind what's going on. That's what we pride ourselves on at Stoller. However, this also tells a story. This tells us that we have a greater health, a higher health plant at the end of the season. And the indications are there from the NDVI values. So that's a really important message. As well as the earnings per acre. So taking cost of application and things like that into account as well. This was also very profitable for this particular producer. So increase of about $2,600 for this particular treatment and almost a $5,000 increase or greater, than $5,000 increase on a per acre basis for this particular grower. That's a very valuable tool in helping us understand performance and ultimately understanding how our products are performing. For my last example, I'd like to also talk about sensors. This example is going to be in an almond crop, again in California. This particular sensor is in collaboration with a company, a very large tomato processing company that has a sub part of their business focused on monitoring systems. Their monitoring systems are focused specifically on water use efficiency. So water use efficiency, they're using it as a tool to stress processing tomatoes so they get the correct color in those processing tomatoes for when they're harvested. So they're using water management as a stress tool, and they're using infrared sensors and canopy sensors in order to understand how much water they need and when they need to apply water to stress that plant to get a favorable response at harvest. Now we're trying to use these sensors in a different way. Now let me explain why. In California specifically, every region of the world has their own challenges and their own demands in terms of what that local government is requiring. But in California specifically, they produce about 2 million acres of almonds, very large almond producing area. There's also very tight restrictions and requirements around water in California as well. So one of the requirements that the state of California has placed on those almond producers is that by 2025, they're committing to reducing the water use in almonds by 20%. So we talked in the very first slide, I said we need to increase production. Well, how are we going to increase production when we're losing some of our tools, such as water, right? So this is a very big topic that's occurring, again, not only in California, it's occurring across the world with fertilizer, with soils, and with water use efficiency. We have a massive challenge ahead of us. These sensors are something that are very valuable in helping us understand how our products are performing when we reduce water usage and what water usage can be impacted in terms of increasing yield. This particular trial, we were very interested in two different parameters that sensor was able to collect for us. Number one is canopy temperature, and number two is air temperature, so ambient air temperature versus what the canopy temperature is. On the y-axis, you're going to see the degrees in Fahrenheit, and we actually have calculated an algorithm to give us a value here. So this value is actually significantly different. At a very high level, our p-value is 0.0014, so we are 99.96% confident that there are significant differences between these two means. What we see here is a standard grower practice. What we see on the right is a standard grower practice plus a Stoller solution. What we're able to do with this technology is actually decrease the mean degrees that plant is exposed to. Most of us well understand that when we decrease canopy temperature, we're also lowering the respiration of that plant, thereby using less water. So this is one tool that we're able to start to understand, and just again an example of how we can use tools like sensors and technologies like we have at Stoller to be able to help solve challenging goals that we place in front of ourselves, like reducing water by 20%. How are we going to achieve that? This is an example of how we possibly can achieve that. Ultimately, again, I mentioned on a previous slide, I want to know what the data tells us. The data told us in this particular trial, we were able to decrease mean canopy temperature for the entire month of July, but also increase yield by over 400 pounds an acre. That's worth a tremendous amount to the California almond industry. So just to wrap up, I have a couple of concluding thoughts, and then I can open it up for some questions if we have a few minutes. I always like to share, especially with audiences like this, and especially when I have the platform, is what's coming next. Again, this talk was just focused on one specific project that we're focused on at Stoller, which is digital ag. There's many projects that we're focused on. There's many challenges that we have to overcome as well. Regulatory concerns or registrations are a big one that our entire industry faces. That's a big challenge about how we register our products around the world, and ultimately working with regulatory authorities to make sure that we have a cohesive collaboration and teamwork in order to provide solutions to producers. Population growth is a big challenge, right? We've emphasized that pretty hard today, and sustainability is going to be key to that growth as well. Many of us are well aware of this topic and all the supply chain constraints that we're facing globally since our global pandemic. That's really just now starting to impact the agricultural segment. It's impacting us pretty heavily. It's also impacting commodity prices very heavily as well. Most of you have probably noticed when you go to the supermarket, the grocery store, cost of goods is increasing. So that's something to be concerned of. That's something to be thinking about. Ultimately, technology improvements and advancements are going to help solve many issues. However, I want to remind us that we can exponentially improve our curve if we work together, right? So I always like to share this, especially when we have a diverse audience like we do today for the Stoller Chair event, is this may be our growth curve, this blue curve may be our growth curve if we work independently. But if we work together, we can transition from a linear model to an exponential model and achieve much more growth in a much shorter period of time if we connect, if we use events like this to talk about our science, our advancements, and help work together to help feed a growing world. Just a few summary messages. First and foremost, the biostimulant, the nutrient use efficiency, water use efficiency, this whole sector has very unique opportunities and a massive potential ahead of us in order to improve agriculture sustainability. I do believe that extremely strongly. Number two is we need to make sure we utilize the lens of a grower. I shared that image of the almond field. I hope you remember that image the next time you're talking with a grower as well, because we need to consider them as the primary driver for product innovation. Third point is that our horizon is bright. I mentioned that a few times. However, there are going to be things that can increase complexity. We talked about those in the previous slide. So just being mindful of those complexities and being mindful of the challenges that we have ahead of us. And lastly, we just need to make sure that we leverage our science, technology, and ultimately connectivity, just like I shared on the previous slide with shifting our curve from a linear model to an exponential model, so that we can move away from the crawl and the walk type of phase and move into the run type of phase, right? So we can increase our ability to connect and increase our ability to provide solutions around the world. I believe that's my last slide, and I thank you for your attention and thank you for the opportunity.
Thank you very much, Ryan, for your presentation. Turn for questions. Okay. Could you please pass the microphone?
As I have seen that you intend to use less water, probably you speak only about almonds at the moment, but this is very important for more massive crops in the United States and all over the world, like all kind of grains. Have you ever thought or have you developed a product which is, when you see that stress is coming or high heat and drought, that you close the stomata on the plants and they keep the water, osmotic water inside, increase the pressure inside the plant of water, then the water evaporation lowers, and the temperature of the plant all over during the stressing period and the activity of the ingredient you apply is staying there.
Yeah, I'll do my best to try to address that. I think I understand your question. The moment of when you try to focus on water use efficiency is extremely critical. I don't believe we have that well figured out yet, the exact moment to try to apply whatever solution it may be to decrease the water use in the plant. Because to your point, if you close the stomata, you're closing gas exchange. And gas exchange is critical for respiration, for light-dependent and light-independent reactions. So there are many impacts that you can have when you close a stomata. If you use that as the primary tool to decrease water use efficiency, you may find challenges there if the moment of that timing is not specific to what's going on and occurring physiologically in that plant. Let's say, for example, if you're trying to close the stomata for a long period of time when the plant is trying to reproduce and it's not able to move sugars, it's not able to move things to fill fruiting structures, that could dramatically decrease the ability to increase yields. Conversely, if it's at a period of stress, and maybe it is more harmful to be doing gas exchange than it is to close for a short period of time, you could actually flip that scenario and actually get an increased yield because you're reducing stress. So I think the answer to the question, if I understand it, is really going to be studying the exact moment and for what period of time do you try to focus on closing the stomata. Does that answer your question?
Yes, because the question was actually, if you close the stomata and look at the weather forecast and you wait 2, 3, or even 4 weeks without any rain,
Yeah.
then these physical problems you explain about closing it will be more beneficial as negative.
Yeah.
And we have developed similar kind of product which have a working period of couple of weeks, so we give them advantage of the plant to stay alive during very high heat and drought stress.
Yes, we have examples, specific examples of that type of topic that we could share with you and talk about some of those different technologies. Some you may have in your country, some you may not. But there are certainly solutions that we could share that could tackle that. Perhaps we could talk about that afterwards.
Yeah.
But there are a few solutions that may work in different technologies that we could at least attempt demonstration trials in your area to see if it's helping target what you're trying to achieve with that particular solution.
Thank you. Thank you very much.
Absolutely.
Any other question for the attenders? Well, I have a question, Ryan. Considering all the devices that you have displayed in your presentation, do you think that they could apply in a global way, considering all different crops realities, or it depends on the budget per hectare that we can afford?
Yes, I think that's a really important topic because I get that question asked quite frequently. I shared numerous examples of different technological tools, and many of them were from California. It does not mean that California is the only place that you can do this types of work. Satellites would be the easiest to access anywhere. The only restriction from satellites is going to be your connectivity. So you need quick internet speeds, you need to make sure you have a good computer source to be able to download all the images and analyze the images. Sensors are becoming more affordable. What's more important with sensors is using the right sensor. That's the most important piece. Drones are a challenge. Drones, I do not believe, are sustainable around the world for many reasons. A, they're very expensive. B, you have to have a license in many countries to be able to fly them. And C, it's very dependent on what particular drone you have and what type of sensor you have equipped on that drone. I think drones are very nice on a local level, but they're not very easy to spread across the world. Ultimately, the sensor, the drone, and the satellite, all that data can talk to one another. So you can build a really strong algorithm. That's what I had a comment in the slide, and I moved past it because I wanted to make a different point. But the comment was, eventually, we will be able to use a satellite image and use that satellite image as a predictive tool because we'll have all the small local field information from a drone or a satellite, or a sensor to be able to tell us with a pretty high confidence interval what the problem is and what a solution could be, whether it's turn the water on, turn the water off, apply nitrogen or don't apply nitrogen, apply a biological or don't apply a biological, and at what rate and at what time and for how long. That's a very big multi-year project. I don't believe anybody has figured out that yet today, but we will be able to do that. It will take probably 5 to 10 years conservatively to achieve that on a large scale, but we are working towards collecting that amount of information. But ultimately, yes, I do believe that you can implement these on a global scale, but certain things may be more easily adapted in certain environments in the short period, but long term, we will get there with advancements in technology. I believe that.
Okay, thank you very much, Ryan. Absolutely. Thanks for your presentation. Well, after this last presentation, we will proceed with the closure speech that will develop by your Vice President of Subsidiaries for EMEA, Mr. Sergio Aguilar, and SEU General Manager, Mr. Mauricio Trigal. Also, Elena Pico, representing the Colegio de Ingenieros Agrónomos de Levante, will join us in this closure event.
Hola, buenas tardes. Yo voy a ser muy breve porque sé que lleváis 2 días escuchando conferencias muy interesantes y simplemente...
So maybe if you speak English, they will translate to Spanish to the team.
She's going to do it va a hacerlo en español.
Because she speaks English as well. There's more English.
Well, I can try to speak English, but I haven't spoken English for a long time, but I will make an effort, okay? So I was saying I'm going to be very short because I know you've been listening to speeches for 2 days. So I represent the institution of agronomists here in this region, and I just wanted to say that it's very important, these ¿cómo se dice? Jornadas? Un apunte? These sessions are very important because although topics as climate change is real and we all know it's happening, we need to concentrate this knowledge which companies as Stoller are developing so that every farmer, every grower can apply it. So in all this kind of investigation, agronomists are very important. So I just wanted to thank Stoller for these sessions. Okay? Sorry.
So, okay, good afternoon, everybody. First of all, I would like to apologize that we're not here the 2 full days. We just arrived from meetings in our head office in the US. But I heard the event was great, and I could hear the last speeches. And first of all, I would like to say thank you very much for Alberto Salbatista, if I'm saying correctly the name, the director of the school. So thank you for hosting the event for us. Thank you very much, Elena, representing the government, the Committee of Agriculture in the government, and the school, I don't know how you say in English, the colegio, yeah, the board of agronomy engineers. And thank you very much for the Stoller Chairs heads that hosted this event. So thank you so much, Loreto Fenoyosa. Thank you, Professor Salvador Lopez. And thank you, Sergio Gonzalez, for this great event. And of course, thank you to our team that has been putting a lot of effort for this to happen. And thank you very much for our customers that came from far away, from more than 20 countries, to participate. And last but not least, thank you to the speakers, the 8 speakers that came from different countries, representing different areas in the scientific approach. So thank you, and thank you. Unfortunately, one of them, Monji, was not present, but also did online. Well, from my side, is just to highlight the importance of this event for our continuity as a institution in Europe. Our business model is based on 4 main pillars, which are surrounded by knowledge. So basically, we're a company that focuses on commercial excellence, where we're persistently creating demand or showing possibilities of solutions to different problems we have in agriculture, all based on plant physiology. We are a people-oriented company, as you saw, empowering plants, empowering people, where knowledge is the main drive of our company. We are a customer-focused company. Here, the clients representing this, where we're focused on true relationship, long-term relationship, which comes with knowledge. So you see all of them are based on this, sharing knowledge to the client to be able to be in the business for a long term with sustainability. And we have an innovative discipline, right? Which is basically based on discovery, research, and synergistics with plant physiology, plant nutrition, and biological technologies, aiming better yield and better quality to the farmers. By the end, all these 4 pillars, they are connected through knowledge. And that's why this event is so important to our business, and to be connected to the science and to the scientific state of the art of what is going on in the world, to be able to bring this to Spain together with the University Polytechnical Valencia. It's a reason for us to be very proud and for us to be very thankful for all of the participants. So thank you very much. I hope you enjoyed, and we're already planning for next year to be together again. Thank you.
Okay, from my side, representing Stoller International, the first thing I want to do is to thank Stoller Europe for making a dream real, a dream that started 2 years ago when we started collaborating with the University of Valencia, the University Politécnica de Valencia, and the School of Agricultural Engineers and Medio Rural. As Mauricio already said, knowledge it is part of our DNA, it's part of our values, but to share the knowledge with people. When after 2 years of COVID, we can have this opportunity to have so many good friends here, attending, supporting, sharing with us this experience. It's very impressive and emotional. So I want to thank Mauricio for leading this year this project and making real a dream that started 2 years ago. The whole team in Stoller Europe did a great effort. We are very proud from Stoller International, very proud of what they did these days. And we thank what they have been doing, because this is one way to spread the message that globally we are trying to. And definitely, this is a clear example of what we are pretending to do, no matter where. This company belongs to people. Belongs to the people. We want to create solutions, but we want to create solutions for the people, for the society. We want to be perceived as a company offering something good for everyone else. And this is important for us. So thank you, Mauricio. Thank you, the team. Thank you, everybody. I don't want to go through all the people that Mauricio already thanked for this opportunity. I want to thank our collaborators from Stoller International that they did the effort also to come here to help Stoller Europe in this event. There is only one company, which is Stoller, no matter where we are, and we feel it like that. And then it's a pleasure for all of us to be close to our subsidiaries whenever we are needed. And for that issue, it is a real pleasure. And definitely, my invitation is, I hope this continues for many years. We continue linked to research centers, prestige universities, and our clients, very attached to our clients, the growers. We all here interested in making the life of our growers a little bit easier, offering them solutions and knowledge. So thank you from myself, thank you from Stoller International for all you've done, and congratulations. Thank you for everybody that was connected. I know a lot of people from all over the world has been following these sessions, and we are also very proud of that. Thank you very much. I hope to see you next year here. Thank you.